Our problem for today is similar to the problem that we had yesterday. We have some objective function that's going to be subject to some constraint. So let's suppose that of all rectangles with a given area A, which one has the shortest diagonal? So we might already know that the answer is a square, which is helpful. We know that we're going to get the shortest diagonal if L and W are equal. So knowing that is only part of it. The reason that I picked this problem is because we already know that. That way we can make sure that our calculations go along with our knowledge. So make sure that those two things match up. All right. Also remember our overall plan. We're looking for maximums and minimums. We take the first derivative, set it equal to 0, and solve to find the critical points. And then we can classify those critical points as local maxima, local minima, or neither. We can do that with the second derivative, or we can do that with the first derivative, checking to see if the function changes direction because the derivative changes sign. All right, let's take a look at what we got. We've got a rectangle, a generic rectangle with a length and a width, a generic length and a generic width. Our constraint is that the length times the width is a fixed area. So rather than having a fixed area of 40, volume of 40 like we did yesterday, we have a fixed area. A is constant, and so the area is our constraint. A is constant. And so here is our constraint. Because if I want the shortest diagonal, I'll just make the width or the length 0, and then the diagonal will be 0, or width and the length 0. So the diagonal is equal to 0, and that's going to be the shortest diagonal. But that rectangle will not have an area of A. So subject to this constraint, how can we get the diagonal to be the shortest? So we'll need a function for the diagonal. And for that, we could just use the Pythagorean theorem because I did say of all rectangles with a given area. So the diagonal is the square root of the length squared plus the width squared. So we'll just use the Pythagorean theorem to find the diagonal. Now, we want to take the derivative of, I shouldn't have called it lowercase d. Let's change the name of the diagonal. To, let's say, something else. Let's call it S. That makes sense. S for diagonal. All right, so we want to find the short S for shortest diagonal. Now it actually works. So we know that the length, the diagonal that we're trying to minimize is the square root of L squared plus W squared. That's our objective. So we're going to do the same thing that we did yesterday. We're going to use the constraint, which is a relationship between L and W, and plug that into the objective to write S in terms of just one variable.
Professor,
Yeah.
I'm not sure about other people, but right now the screen's black and just like showing a corner. But I'm not sure if it's just me or is everyone else seeing it too.
Is
Oh,
anybody...
never mind, it's fixed now. It's fixed now.
Okay. All right, so right now S is in terms of two variables. We need to get S in terms of one variable. We need S in terms of one variable, so we're going to use the constraint to get S down to one variable. All right, L is the least convenient one to write, so I'm going to solve for L in the constraints. L is A over W. And I'm going to replace the L in our objective with A over W. So S, for a rectangle of fixed area, the diagonal will be the square root of A over W squared plus W squared. Now S is in terms of one variable. We have used the constraints to get our function S in terms of one variable. Any questions?
Professor, I do have a question. So the point of solving for L is to get rid of a variable, right? But now that we have A too, wouldn't that make it still two variables?
A is not a variable.
Oh, it's
A
constant. Never mind.
is the fixed given area.
Understood.
So now S is just in terms of the width, and A over W is how big the length is going to be for a fixed area. So here's our objective function. It's got this big square root, and we definitely don't like that. I'm going to try to write this with powers of W, but the problem is all this stuff is being raised to the 1/2 power. I could write this as A squared W to the -2 plus W squared, and here's the inconvenient part. This is all raised to the 1/2 power. So I'm kind of just getting things ready for us to take the derivative. And the thing that we don't like is that this is raised to the 1/2 power. So I probably shouldn't build in such prejudices, but this 1/2 power, this square root is going to cause problems. So, spoiler alert, this square root is going to make things messy. What do we need to do? We need to take the derivative, set it equal to 0, and then solve. So I need to find S prime. Now to maximize or minimize a function, we solve S prime equals 0. So I need S prime. And W is our variable. Remember, A is constant. So I have to use the chain rule. I have a 1/2 times A squared W to the -2 plus W squared to the -1/2 times the derivative of the inside with respect to W, which is going to be a -2 A squared W to the -3 plus 2W. So here we are using the chain rule. Inside is A squared W to the -2 plus W squared. And then the outside function is to the 1/2 power.
Professor Lynch, how did you get on the derivative -2A squared W negative power -3 plus 2? Where that -2?
So I have to take the derivative of the inside function. So the derivative of A squared W to the -2, W is the variable. So I multiply by -2 and then subtract 1 from the exponent. A squared is constant.
Oh, okay, I see it.
And we're taking the derivative of w to the -2.
Yes, I see it. Thanks, Professor. I see it now.
So a squared is a constant multiple. And we're taking the derivative with respect to w of w to the -2. But the a squared is a constant factor. So S prime is pretty messy. Got this little bit of a mess here for S prime. This is going to be our numerator. This is this a squared w to the -2 plus w squared is raised to the -1/2 power. So this function looks like this. Any questions? We got to find the derivative because we're going to set the derivative equal to 0 and solve. Now let's take this derivative, set it equal to 0 and solve. Remember, we're looking for w. Once we have w, we can figure out what L is supposed to be. And then we'll be able to figure out what kind of rectangles that we're dealing with, even though secretly we know it's going to be a square. So to optimize the function, we solve S prime equals 0. So remember, our goal is to solve S prime equals 0. So I'm going to set S prime equal to 0, and then we're going to solve. Now, what will make the S prime equal to 0 is when the numerator is equal to 0. We have a little bit of a concern because we're divided by the square root of a squared w to the -2 plus w squared. We can't multiply both sides by that square root if that square root is equal to 0. So since we're looking for the minimum length of the diagonal, and we've already ruled out the case where the diagonal is equal to 0, we really just need to concern ourselves with the numerator. So if S prime is equal to 0, that must be because the numerator is equal to 0. We're not going to worry about multiplying both sides by this square root. So if S prime is equal to 0, that means that the numerator, -2 a squared w to the -3 plus 2w is equal to 0. If we have a quotient that equals 0, it's because the numerator is 0. If you're thinking in terms of limit, if the denominator is going off towards infinity, then S prime might be approaching 0. But take a look at the denominator. The denominator is just the length of that diagonal. And we're not concerned with the case where the length of the diagonal is headed off towards infinity. We want the smallest diagonal, not the longest diagonal. So we only care that when the numerator is equal to 0. But now we got an equation. Let's solve it. I'm going to put the negative stuff on the other side, and I'm going to write 2w is equal to 2a squared over w to the 3rd. And then I'm just going to hit this with the algebra stick for a while. I'm going to get rid of those 2's. I'm going to divide both sides by 2 because 2 is not w. I'm not concerned with the case where w is equal to 0 because then I won't have any area at all. That's beyond the scope of this problem. So I can multiply by w to the 3rd. and say that w to the fourth is a squared. And now we're finding out that we're dealing with a square. If w to the fourth is a squared, then w is a squared to the 1/4 power, which is a to the 1/2 power, which is the square root of a.
Firstly, how did you get the 2a squared divided by w to the power of 3? Where that w power of 3 coming from?
It's just this term. I took this term and added it to both sides.
How that w power of 3 becoming divided?
That's how negative exponents work. W to the negative 3 is a 1 over w to the third.
Oh, yes, right. Okay. Got it.
So we find that w is the square root of a. Now we can take this back to our constraints, and we find that and we remind ourselves that L is a over w. And since w is the square root of a, L is a divided by the square root of a. So L is also the square root of a. So this confirms our suspicion that a square is a rectangle of fixed area that has the shortest diagonal. Oops. Because we found that L and W are equal when we minimize the area.
Professor Rich, you don't mind explain the w to the power of 4 equal a squared, and then the bottom w equal, how you get to those answers?
I raise both sides to the 1/4 power so I can cancel out the w to the fourth. So if w to the fourth is a squared, I want to raise both sides to the 1/4 power. 4 to the w to the fourth to the 1/4 is w to the first, and then I have a squared to the 1/4 power.
And then you have a to power to 1/2.
Yeah, a squared to the 1/4, we multiply the exponents. So a squared to the 1/4, it's just 2 times a fourth, which is 1/2.
I will review that later. Thank you, Professor Rich.
X squared to the third is x to the sixth. We multiply the exponents.
Professor?
Yeah.
It doesn't click in my head how a over square root of a is equal to square root of a.
Square root of 9 is 3. 9 divided by 3 is 3. Always just drop in numbers. A is the square root of a squared. We could also think of it that way. A is the square root of a squared. So if we have a over the square root of a, that's the square root of a squared over the square root of a, which is the square root of a.
Thank you.
Also, when in doubt, remember a is constant, so just drop in a value for a. So if a is 25, the square root of 25 is 5. 25 over 5 is 5, which is the square root of 25. Any other questions? How's everybody, okay? All right, so we had to do some talking around this, the s prime with this radical part, because this square root is going to make things messy. I want the first derivative to equal to 0. That means either the numerator is equal to 0 or the denominator is headed off towards infinity. If we look at the once again, if we look at the denominator is just 2 times the length of the diagonal in the first place. So the denominator is just the length of the diagonal. If that's going off to infinity to make the first derivative equal to 0, we're not concerned with that end because we were trying to minimize s prime, or sorry, we're trying to minimize the length of the diagonal. So we're not concerned with the case where the diagonal is headed off towards infinity. So the context of the problem tells us not to worry about that case and just take the numerator and set it equal to 0. That's how we're going to get the derivative equal to 0 in this case. Another common trick is when you're trying to minimize a distance, minimize the square of the distance. That kind of drops off this square root business, which is one of our 3 great tricks of mathematics. Add 0, multiply by 1, or switch to a smaller problem. So when s is the square root of a over w squared plus w squared. So this is the length of the diagonal. A common substitution, because this square root is sitting over the whole thing, a common trick is to, instead of minimizing the length of the diagonal, minimize the length, minimize the square of the length of the diagonal. Because if you make the square of the length as small as possible, that will mean the length is as small as possible. Oh, I got to speak in terms of clickbait titles. One simple trick for minimizing a length. Clickbait. 2021, I should use more clickbait. One simple trick for minimizing a length. Minimize the square of the length instead. The reason that you want to do this is that it gets rid of the square root part that made things messy. So instead of minimizing the length, minimize the square of the length. Now we don't have to use the chain rule. So instead of minimizing the length, minimize the square of the length. We can drop that radical part and we'll have a squared w to the negative 2. We'll just have this part. Then when we go to take the derivative, we'll have s squared. Take the derivative of s squared, and we'll just have negative 2a squared w to the negative 3 plus 2w. This is the part that we were setting equal to 0 anyway. This works because we don't have the square function for length, since everything is positive. If the length is larger, the square is larger as well. Any questions? So setting the derivative of s squared equal to 0 in solving is exactly what we did in the previous problem anyway. So this is kind of a common trick. The reason I wanted to point this out was we just did this yesterday in Calc 3. The problem was to minimize the length. So we minimized the square of the length to make our calculations easier. And then just remembered at the end to take the square roots when we actually found the minimum length. Any questions?
Yes, Professor Lich. The first one we just did, the previous one,
Yeah.
the power rule, correct? We convert the square root to the power,
Yes.
and then we get the derivative. On this one, we use the Pythagorean or something, the shorter. Is that right?
No, in this since we're looking at the square, we got rid of the square root parts. Minimizing the square will minimize the length. The square of the length will minimize the length. So that kind of gets rid of the square root parts. And so we're just looking at the stuff inside the radical. Now we didn't need to use the chain rule. I didn't need to, there's no square root there anymore. So I didn't need to do a 1/2 stuff to the negative 1/2.
So this is the answer? No, right? This is
not the answer.
Oh, okay. All right. Yes,
The answer is W is equal to the square root of A. And so then L is also equal to the square root of A. So squares have the shortest diagonal of rectangles with a fixed width. Any other questions? All right, so this is a trick, and a lot of times when we're minimizing lengths, because the lengths come from the distance formula or the Pythagorean theorem, there's going to be a square root involved. That's going to make things messy. So when you go to minimize a length, if you start looking at solutions, someone might throw away the line, well, we'll minimize the square of the length instead. And I just want to let you know that is a common thing to do. And it's because of that square root business. But I want to do the problem with the square root in it to show you that it'll work out just fine. Any questions?
Yes, actually, on this one right now. So if we work it out, so we're looking for L equals square root of A. Am I right?
We are exactly at this point.
Yes.
We're in the exact same situation.
Yes. So
we're going to take this derivative and set it equal to 0 and solve.
And then the answer will be L equals square root of A, correct? That's the answer.
The solution to the equation will be this W equals the square root of A. It's an equation in W, and W equals the square root of A is the solution to the equation. Once we have W equals the square root of A, we have to go back and use that W to find L. A divided by W.
I will revert. Thanks, Professor Lich. I will revert again. I understand that. Thank you.
All right. So the original problem ends right here. We found out that squares have the shortest diagonal of rectangles with a given area. And that makes sense with our intuition. We try to make things as circular as possible, just like we did with the cylinder yesterday. We tried to make it as circular as possible. Same thing with this square. We try to make this square as circular as possible. That's going to be an efficient use of the area. All right. That's going to do it for today. We'll have a new problem to look at tomorrow. Everybody have a good day. And thanks for playing.
Thank you, Professor.